Hello. Testing 1 2 1 2. Okay. Okay, we start. Ready or snack? Yeah. Welcome back. So we have a math help center on Tuesday, Wednesday, Thursday, Friday, 2 to 4 p.m. So if you need any help, you can go to the math help center if you can't find me in the office hour. Or if you need help outside my office hour. So any question from last week lectures? Anybody have any questions want to ask? Q&A section. By the way, I want to remind you next week is a quiz one. Okay. If there's no accident, we'll do quiz next week. Any question from last week? Was I close the if not, we will go into this week material. So this week material I want to warn you is a bit fast. So make sure you, if you can't catch up, please raise your hand and ask. Okay, don't be shy. If I say something too fast or you don't understand, please ask. Yesterday, a lot of people stuck. Okay. Okay, just to remind you from last week, we talked about tautology, which is a compound proposition that is always true, and contradiction, which is the opposite, a compound proposition that is always false. And then I show you two general examples. And then how to show something is a tautology. You consider all the choices and then prove that it is always true. And on the other hand, for contradiction, you show that it's always false for every choices. Okay, this is from last week. Okay, so this week we will go into logical equivalence. So what's logical equivalence? So logical equivalence, when we talk about logically equivalent, we refer to two compound proposition. Okay, we say that two compound proposition are logically equivalent if P, if and only if Q is a tautology. Okay, and in other words, we also can say that P and Q are logically equivalent if they have the same truth values. Okay, so meaning P and Q have the same truth values. Okay. So a good exercise is to show that these two are equivalent. Okay, let me erase this. Okay. So for example, I want to show that not P or Q is logically equivalent. So this is the notation for logically equivalent. Logically equivalent to not P and not Q. Okay. So what do I do? So I draw the truth table. Okay. So draw the truth table. Wow, what's wrong with this iPad again? I think this table has some problem. Right? Let me try writing on here. Can I write on here? I think the table got problem. I write on here. There's a table when I use it, it's something unnecessary. Sorry, I see you cannot. Okay, sorry. That table got problem, last one also got problem. Okay, so okay, so we want to show not P or Q is logically equivalent to not P and not Q, right? So what I show you, what I did here in the definition is show that the two propositions are logically equivalent if they have the same truth values. Okay, let's check. Let's check whether they have the same truth values or not. So I already list out all the possibilities here. Okay. And then I conclude what is not P, not Q. Then I want to do P or Q. Okay. P or Q. What's P or Q? Anyone tell me? True what? True. True. False. Okay. Not P or Q is. And then not P and not Q. False. Not. Okay. Let's see. So now we want to find not P or Q this column. Okay. If and only if this column, which is true, 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 true. Okay. So there's two way. So two way to show. This is the okay. Let me label this. So this is the first way. This is the second way. So this is the second one. And then this is the first one. Okay. Okay. Any question? Now we have to go fast because quite a lot we need to cover today. Okay. And then one name I want you to remember today, you must remember today before you become a logic student. This is a De Morgan law. And De Morgan's law, what it does is when you negate a disjunction segment, you become a conjunction segment and then negating what proposition here. Similarly, we got another variant which is not P and Q, and you should guess which is not P or not Q. Okay, so similarly, you can prove this. We should prove it. So exercise, go ahead and do. Exercise, prove this statement here. Okay, that's not it. Proof. Using the same way. So same method here, exactly the same. Okay. No question? No question? Okay. Next. I have to clean my stuff so I can sit here. I have a lecture note. Maybe next time clean up. Okay. So now we got this table here. So the table here, maybe the first thing you ask me, you want to memorize or not? No need to memorize. Just understand. Okay. If I want you to use in the exam, maybe I will provide you a list or hint, but I won't tell you how to use it. Yeah. So how to understand this list here? So this is actually not too strange to you. It is actually quite close to the number system. Okay. Where you have the addition, multiplication. Okay. So the O here, you can think of it as a addition, and then N, you can thought of it as a multiplication. Okay. And then what you have in this identity law, so when you take a conjunction with true statement, so this is a true statement, okay? This T is a true statement. Always true statement. F is a always false statement. Okay, so in conjunction with a true statement, you always get back your own statement. So like in the number, you have like 2 add to 0, you always get 2. Okay, like 2 multiplied by 1, you always get 2. Okay, this is the identities, additive identities and the multiplicative identity. So similarly, these true and false will be the identity element. So domination laws, meaning these true statement dominate over the usual statement. Okay, and then you should notice this O and N. And then all this sign here, logically equivalent. So that means you can do the same truth table. Okay, do the truth table and then show that they are logically equivalent. And idempotent is something that square to itself. Okay, so you see, so P or P, you give it yourself. P and P, you give it yourself. Okay. And double negation law, actually, I used it last week's secretly. So actually, you need to show that is a negation of a negation is, you go back to the original proposition. This is not, this is should be also familiar to you, is the minus 1 is 1, something like that. Okay. So commutative laws. So commutative, so A, so like 2 plus 3 equals to 3 plus 2. Okay, so commutative. Associative, I talked about this a bit last week as well. So you can do your bracket differently. You can do it at the front first and then do it together, or do it at the back first and then do it together. This is also happening in the number system. Distributive law, yeah, distributive law. So you see, you can open the bracket, P or Q, okay, open the bracket. This is also like the number system. Okay. De Morgan's law, just now I proved it to you. You should know this. This is the only law you have to memorize today. De Morgan's law. Absorption laws, P or P and Q is P. So Q is nothing. P and P or Q is still P. So this is kind of important if you are writing code. If you have a lot of condition you want to consider, actually that condition is useless. So you can reduce your code very efficiently. Okay. And negation laws. Negation law is the one we touched last week. So we prove that P or not P is true, and then P and not P is false. Tautology contradiction. Okay. Okay. If any question, just stop me. Okay, next. Okay, there's two very important one you need to know. First one is P implies Q. Okay, P implies Q can be written as not P or Q. Okay, use or negation to express. So if you realize that last week I didn't teach you what is the negation of P implies Q. Okay, but with okay, and then not P implies Q. With this logical equivalence, I can write it as not P or Q. Yeah. See this one coming out again. And then so not disjunction. What law do you use? Huh? What law do you use? The only law you need to memorize today. De Morgan's law. So you have to use De Morgan's law. So what's De Morgan's law? Okay, use it here. So okay. So okay. So De Morgan's law. So not a conjunction become a sorry, not a disjunction become a conjunction, and then you not the both not P wait, let me try again. If not, I really want to move down. So not P and not Q. Okay. So double negation law give you not P become what? Yeah, right. Okay. Okay. So that means if you want to show that P implies Q is false, you need to show that P, given P, you have not Q. Okay. This is how you show something P implies Q is false. Okay. You need to have P and then not Q, and you will show that this is false. Okay. Yeah. And then second one, do you recognize what is this? Do you recognize what is this? You swap the position and then put negation. It's a con what? Con what? Converse or contrapositive? Huh? Converse or contrapositive? Contrapositive, yes. Okay, so actually you can show that these two have the same truth table. Okay, so if you want to show that this is true, then you also can show that not Q implies not P. Okay. Similarly, for this, if you want to show P implies Q, you also can assume, you also can find not P or Q. Yeah. And then let's see. So the next, all these things you can derive yourself using the truth table. Maybe not so important, and some of it is in the tutorial sheet. And then this one is also important. P, if and only if Q. Okay. Actually, is P implies Q and Q implies P. So it's the P implies Q and it converse. Okay. This is also interesting. You should show it yourself. Okay. Okay. Next. Okay. Okay. Next. Show that P implies Q if and only if not P. Okay, I already put some table up. So anyone can tell me what's P implies Q? Hmm? True? False? True? True. Okay. How about this? Huh? True? False? True? Okay. So we want to show these two are logically equivalent, then we work out the truth table and then see that they have the same truth value. Okay. Okay. So how about this? Okay, let you try first. You can ask your friend at the side or you try first. I give you 2 minutes. You can discuss with your friends how to show this. Okay, so let's see. So first, okay, there are 2 ways to solve this question. So first is to use the truth table method. Okay, second is to use the algebra method. Okay, you want to see the first one first or the second one? Huh? First one, okay. So first one is the traditional method and then showing from the definition. Okay, so similarly, let's start with the truth table. Okay, the first one. Maybe I will it's easier. This is a P, this is Q, not Q, not P, P implies Q, not Q implies not P. So I got what combination I got? I got true, false, false, true, false, false. So not Q is a false, true, false, true. Not P is implies Q is false, true. Not Q implies not P is false, true, true. Yeah. So they have the same true values. Okay. How about algebra? Anyone try algebra method using the table I showed you just now? So P implies Q is equivalent to not A, not P or Q, eh? Is it? Okay, let's check, See? P implies Q is not P or Q. Okay. Okay, so how do I go here, go from here to here? Okay. So maybe we can do backward. Okay, we do backward. Try backward. So what is not Q implies P is what? Huh? Not Q implies not P, right? Is it? See, P implies Q is not this one or this one. So not this, sorry, or not P. Okay? Everyone follow? Everyone follow or not? Which one? You mean this one? This one? Why is it not Q? Because you see, the definition of P implies Q is not the first one or the second one. So I use the definition, not the first one or the second one. Everyone follows? Okay. Okay, so next, what do you get? Going backward, not Q, you get? Huh? What? Hey, no lah. Emojis have to use for conjunction and disjunction. This is just not, if you confuse, maybe like this, right? Not Q like this. Okay, so not Q, you get Q or not P. So are these two the same or not? Why? Because they commute. Okay. Okay. So it's commute. Okay. So the commute. Okay, coming from this word. Okay, this is the root. Commute, they commute. Okay. Okay. Yeah. So if you know this, then this is, I think it's faster sometimes. Yeah. Okay. So next, this one. This one, I leave it as an exercise. Or anyone want to try it on the board? If not, we leave it as an exercise. I want to go to the next chapter. Anyone want to do? No. If not, we leave it as an exercise. Okay, we leave it an exercise. Next. Okay, next we're going to quantifiers. Okay, now our proposition will include variables. It's like a function. So one sentence, like we group a lot of sentences together. Group a lot of sentences together. How we group the sentence together? So definition. Okay. We got a sentence PX. Okay, PS is a sentence. Okay. involving the variable x. Okay, and then we call P predicate. Okay, and S is the subject that can change. Okay, we can change the subject depend on where we pick it, like where the set or the space we choose. Okay, for example, the space can be student in this class or student in the university or every woman or every male. Okay, depend on the option. So P is the predicate, S is the subject, and also we want that this PX is actually a proposition. Okay, we can say that it is true or false when X is specified. Okay, we will see in a minute what does this mean. Okay, and then the set that S leaves. So I won't tell you what exactly what a set is, but we will do it in the second chapter. For now, you can think of set as a collection of objects. It's like a space. You can think of it as a space. Like all of you now are in a classroom, and classroom is a space. Lives in, wait, okay, we call in, live in here is for the domain or domain of this class. D. Okay. So for example, suppose, yeah, suppose X is in a, okay, this notation is integers. Okay, later I will explain furthermore what integer is. For now, you can think of it as the negative number plus the positive number. Okay, X is greater than or equal to 0. So Px in this case is X greater or equal to 0. Last week, remember we said that this itself is not a proposition, right? So what? Because we haven't specified what S is. So now this week we consider this kind of sentence, and then we will see what's the truth value when X is specified. So this part is the predicate, and then this part is the subject. Okay. Subject can change, predicate cannot change. So let's see. So what is P1? Okay, P1 is 1 greater or equal to 0. So is it true? True. Okay, good. Let's say we check P at -1, which is -1 greater or equal to 0. Is it true? False. Okay. So you see, so it depends on where you substitute the values. Okay, and run and follow. Okay, we not only want to just look at one variable stuff. So Px usually we call a unary predicate. So it's uni, so it's one predicate. Okay. Sometimes we want to consider more, maybe up to n dimensional, s1 to xn. And this will be called the n-ary predicate. Okay. Okay. So next, I want to write some examples of domain. Okay. Example of domains. Maybe you've seen it before, but maybe you are not introduced formally. So first is the natural numbers. Okay, my natural numbers will be starting from 0. Some people will start from 1, 2, 3, 4, 5, start from 1, because they say that when humans start counting, they start counting from 1, not 0. But I choose 0 because there's a piano axiom that build the natural number starting from 0, empty set, using set theory. Maybe we could talk a little bit in the next topic. Okay, so sometimes people will write natural number greater or equal to 0 to emphasize the natural number has 0 in it. And also next, the integers. Okay, the integers we write as z. Okay, so this notation is like n both and z both z. Okay, so instead of integers we have the negative number. Okay, so the reason we introduce the negative is because in the natural number, if you try to add out this number, you get larger and larger, right? But how do you get to 0? Is to add the negative number. So this thing will form a structure called groups. Okay. Okay, next. So next is the rational number. Okay. So the rational numbers. So rational numbers are the fraction, so the ratio of two integers, right? So something like this, or this count, okay, right? Okay, fourth is the irrational number. Okay, what are the irrational numbers? So irrational numbers are the numbers that cannot be expressed as the ratio of two integers. Of course, there's a extra condition here, n cannot be 0. So anything divided by 0 is undefined. And there's some story of the undefined stuff. So cannot be. Let's make sure it's not integers. So for example, you have a pi e square root 2. Okay, so there's a story here. So about the square root 2. So during the Greek times, Greeks, Greeks. So Greeks time, they only have number up to rational number. They think that these are all the numbers already. Okay. They if you know the Pythagoras theorem, you know what the Pythagoras theorem is? What's it? Tell me what it is. Very good. A squared plus b squared equals c squared. So let us look at this geometry. So Greeks like geometry a lot. So what's the hypotenuse? Square root 2. Okay, so Greek study this square root 2. They think that this square root 2 should be a rational number because they think that mathematics is beautiful. Yeah, it's beauty. So beauty means there's some pattern. Okay. Square root 2 should have some pattern, 1.1413, so. But in fact, there's one guy, there's one person in that area, show that square root 2 is actually irrational, which means you cannot express as the ratio of two integers. And then the student from Pythagoras or they are called Pythagorean. They even kill the guy that proved that this is spiritual. Yeah, so this is a set theory. That's basically set stories. Right? So yeah, and so this is the first proof I learned in pure maths class. So I think you guys also should see it on point. Maybe we'll do it next week. Yeah. Okay. Proof by contradiction, set story. Okay. And then this pi also coming from geometry consideration, this pi. So when you study the perimeter, the relation between the perimeter and the radius of the circle. Okay. Yeah. So in fact, irrational number has a lot more than rational number. Although we only like identify a few useful ones out. So next one is the real number. Real number is the rational number together with this is union. So for now, you just need to know that we combine these two set together. I don't even tell you what's the definition of set yet. Okay, so we combine these two numbers is the real number. So it's what you use daily now is the real number. Okay, and then the next level is the complex number. If you have learned it a little bit. Okay, complex number. Something like half plus I minus I, 3 or something. And this one, sorry. Yeah. So we still have two more system is I forget what's the name. Quaternion, but not important for this class, just for your own knowledge, right? So, yeah. And I think there's another one, quaternion. I don't know how to spell. You can find out. Okay. So this one is like I, J, K, and then this should be more. Yeah, but not important, but just for your information. Maybe next time we'll pick something more interesting theory for them. And I think they proved that these are the only number you can be. Okay, so the important one for this course is up to here, the furthest. Okay. So what you need to know from this example, is to know what number live inside this domain. Okay. If I ask you integers, you should know that there are -2, -1, 1, 2 inside here. And when I ask you rational numbers, you should know that there are fractions inside here. Okay. And then sometimes I have some terminology, for example, positive integers. So what these positive integers mean? Number that are greater than 0. Negative integer are number less than 0. About non-positive. Non-positive one is the number less than equal to 0, include 0. Okay, non-positive. So negative plus non-positive one. Non-negative is what? Huh? What happened? Great. Second. Okay, greater than or equal to 0. Yeah. Yeah. Okay. Yeah. So yeah, these are the domain of this course that you need to know. Okay, next. Okay, definition. So let's define some statement study. So first of all, we have universal quantifier. So when we talk about px, we need to specify x, right? So this is one way to specify x. So this is for all values of x in the domain px. Okay, so I write the notation now. It's easier. So this is for every x in B, px is the s for every x in B. Okay, so this notation here actually is an inverted A. Invert. So you A, you invert it. So why they have this symbol here? It's because in the old time they use the typewriter, typewriter, and then they can put it in and then typewriter. So at that time they just pull the A button out and then turn it around and then press it. Okay, because there's no special keyboard for mathematician, so they just make use of the button. Okay, so this is how this A comes from. So why use A for all? Because it's for all, right? For all values. So we use A, capital letter A. Okay, and then definition. So this A, this inverted A, we will call the universal quantifier. Okay, so there are a few ways to say it. We can say it for all, for every, and then for any, okay, or given an x, and then something word. Okay, let's do example. Okay, for every x in R, consider the statement sentence s plus 1 greater than x. Do you think it's true or false? True or false? Huh? True. Why true? Because what? Because what? Say again. I don't know. Who's you don't understand? But you say true. Who say true? Who say true? Why? Okay, because a number plus one is always greater than the original number. I think that require proof. Okay. Okay, actually if we start out number system properly, we actually have to prove this. But here we can do one trick is because one is greater than zero. So if we add x to both sides, you will get x plus one greater than x. Okay. Okay. Okay, I want you to notice here, this x here, okay, this x here, I already take a specific x from R, okay? This means in my mind, this x is either 2, 3, or half, or 2 half, one number. I take one number and then add it on both sides, okay? And then I do it for every R. Any R I pick, this word. So that's why we prove that for every x, in R, x plus 1 greater than x. You get what I mean? So the x here is a specific number in my mind. Can understand or not? Can. Okay, let's try. See if you get it next. Okay. So next we make another definition. So if we want to say that For every x, px is not true, we just need to find one x such that px is false. And then such x is called a counterexample. This is what we did in the first week, right? That every number greater than 1 is less than a million. And then we found that 2 million is a counterexample. Yeah. Okay, 9:50. Maybe we take a rest 10 minutes and then we come back.
So 回答不出来，就是要 Q 去往题啊。我们要往上推的时候，它这个符号就是变从 if 变成这个，这个就只是跟着吧，直接推。
呀，至于这两个什么关系，就是要用这个 truth table 来。
truth table 就证明了。
呀。
哦，
或者说，如果你要字面上说的话，你就看P implies Q，就是 OK，这个句子怎么说？对，either not P 对，或者 Q 对，或者两个对。
嗯，
所以你想一下，如果 not P 对的话，not P 对的话，这个永远是对的。
对，那 P 对
如果 Q 对的话，这个也永远是对的。
，Q 对的，Q 对的话，对，
对不对？对，not P 和 not Q 对的话，这个也对嘛。
哦，
所以你就
明白了，
这样从这里推过去，这里推过来。但是我这样推来推去也是等于在说这个。
就是 truth table。所以很多概念其实就是 truth table 先给一个基础，然后我们懂了大概再反推啊，就 algebra method 的时候可以用。
algebra method 就是说它已经，怎么说呢？它就是已经，你就不用每次都要回去出 table，
哦，对，
这样。比如说，
要碰到 algebra method
嗯哼，
要去想那个，
要去想一下，对对对。
那
如果
推
不常用就要想。
这个刚刚讲要推的就是我们可以根据这边的属性来找。
应该不行，因为我没有告诉你怎么这一个跟这个的关系嘛。我没有告诉你过两个箭头跟这个有什么关系。你明白我讲吗？就是我只告诉你一个箭头跟有关系吧，但是我没有告诉你
两个
两个箭头。但是这个告诉你什么？这个告诉你两个箭头跟一个箭头有什么关系，然后你知道一个箭头跟的关系，这样你就知道
两个
两个箭头跟和
对
n 的关系。
所以还是先要用 truth table 推一遍的。
Yes，因为这是第一次你让
第一次
他跟其他人是
，OK，
对
好的，
那请问一下那个
Yeah
我看你写的这个是两横，
哪一个是
然后
两分？
这个有的时候会写两横，
其实
一个
是一样的，
一样的。
样。
OK
我习惯两横，但是有时候看到书我自动变硬，
OK
但是一样的。
OK OK。
然后我知道他们讲那个符号，
对啊，
就是在哪里？在这里。是这些符号，他们讲会有不同，
什么是叫做有不同？
他们跟中国学的，
他们是这样的。
就可能他只是这样子了，后面一分那个。
OK，因为没有我们就 block 它吧，因为如果通常我们写在是这样，对。
他们的 complex number 就当做 C
明白了，对，也有啦，也有收音的，那我们不要看的。我们打那个 latex
啊，比较方便的。
比较好看，我觉得。
然后 ration number 是这样子的时候，是 Q 还是
rational 其实你也可以 Q 是
Q 来的？
但是没有，I mean 你可以来这样，可以这样，就 Q 然后就加深一下
Q 来的。
就你可以 Q 了，然后加深，其实它是 bold 了，这个是 bold 来的，bold
这样子。
对。
Okay. Let's start. Let's start. Okay, next. Ready? Yes, okay, good. So next, so the existential quantifier, okay, of Px is the segment that exists and another x in the domain such that Px. Okay, so the notation we write is E, inverted E, okay, inverted E that exists, so E capital X that exists. Okay. So this thing we will call the existential quantifier. Existential. Okay. So sometimes we will write there exists, there is, and x1, or we can find one. Okay. One is enough. Okay, at least one. Example, at least one. Okay. So for example, there exists an x in R such that x squared equals to 2. True or false? True or false? True or false? True. Why? Take x equal to
square root 2.
square root 2. Okay, take x equal to square root 2. Then x squared is 2. In fact, there are two of them. You also can take x 2 equal to minus square root 2. Okay. You also get x squared equal to 2. Yes. In fact, there are these are the only two. Those your degree of freedom is 2. So at most 2 groups. Okay. Second. Yeah, so this square root 2 is coming from the Pythagoras right angle triangle. Okay, second. There is an x in R such that x squared equal to minus 1. True or false? False. Why?
Square root can be negative.
Yes, very good. So, a square real number is always cannot say positive because 0 square also 0 is non-negative. In other words, for every x in R, x squared is greater or equal to 0, which is strictly greater than minus 1. Okay. Okay, in fact, this is the starting point of complex number. So just now I told you about complex number, right? So, right. So algebra, so the algebraic person, they want to introduce a root for this polynomial. So they let I to be the root of this polynomial, which means I squared equal to minus 1. Okay, this is how we get the complex number. And then complex number is already proven very useful, such as in the E&E. E&E is not electronic and electric and electronic engineering. I think computer science also uses it. Okay. Okay, next. Any question or no question? So yeah. Okay, later we will talk about negation. Okay, negation of this thing. So it's actually this. Later we'll see again. We'll come back to this. So in summary, Okay, in summary. So if you want to show that for every x, px is true, you need to test it for every x. Okay? You need to show it is true for every x. Sounds hard, right? But if you want to show that this statement is false, you just need to find one x such that ps is false. Okay. So for this kind of statement, to show it is false is very easy. Just find one x such that it is false. But to show that it is true, you need to check for all x. Okay. How about this? There exists an x such that px. When is it true? Just found one is enough. But just now, there's one example we found two, which is good also. But to show that this statement is false, you need to test it for every value in your domain and then show that PS is false. Only then this statement is false. Okay. Yeah. So I go to the next slide. So example, proof or disproof for every x, positive real numbers or non-negative, show that x cubed greater or equal to x squared. Okay, try spend 2 minutes, try prove or disprove it. You can discuss with your friend. 2 minutes. At the same time, I'll pass down the attended list and pass around and sign. Okay, let's discuss a strategy, okay? Strategy. Okay, strategy. For example, maybe I also don't know whether it's true or not, so I need to test. That's right. Suppose I want to show that it is true. That means for every x in the non-negative part, I need to show that s cubed is greater than or equal to s squared. Okay. Let's try first x equal to 0. What do I get? 0 greater than equal to 0, which is true. Okay, let's try, how about 1? 1 cubed is greater than equal to 1 squared, which is also true. S equals to 2, 2 to the cube, greater than equal to 2 to the square, which is also true. But there are infinitely many numbers I need to try. I don't know if it's true or not. Maybe true. So many, like 3 of them is already true. Alright. So if it is false, then I need to find x in the same domain such that s cubed is less than x squared. Do you think I can find one? Like what? -1. -1? -1. Hey, no. Wait first. So he say take, I think this is a good example. So take x equals to -1. -1 cube is less than -1 squared, which is -1 less than 1. But x doesn't live in R greater than equal to 0. Right? Yeah, so you take out of the domain already. So this one cannot work. Okay. I purposely choose the domain one. Okay, so can anyone find some x or not? Huh? What? 0.1, 1/2. Okay, I heard the same thing. I heard 0.1. Okay, take 0.1 or 1/2. Okay, so how to verify this? Okay, so I'm not sure you still remember or not. I think in your high school or what, you learned something like this. And then you factorize. Okay, and then you do what? The table thing. 0, 1, and then x minus 1, x squared. Plus, 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 minus, minus, plus, minus, minus, plus. Remember this or not? So you need to have x is in between 1 and 0. Okay, to give this. Right, remember? Remember? I also just learned from my foundation classes. But I got another geometry proof. So this is algebra proof. So I got a geometry proof. Okay. This is how I originally think of this question. So in this geometry proof, I should sketch these two curves. So I sketch the y cube curve. Sketch the y cube. Okay, and then how about the y square curve? So the y square is like these. Y square is actually very not nice. And let me do this normal bit. But this is the one. Okay. So this question is only focusing on the first quadrant. Okay. Focusing on this quadrant. Okay. Okay, let me color it so that it's more standing up. So let's make red. Okay. Next, this is one. This is going control. One. Okay. Okay. So let's do proof algebra proof. Okay, next. Next. This one later. Do another thing first. Okay, the next one I want to introduce is the uniqueness quantifier. Uniqueness. Okay. So uniqueness quantifier will have a exclamation mark beside E. Okay, there's only one. So very, if Malaysian to say very kanchong. Very this. So there's a unique one. Only unique one, just one. So the notation we will write there's this unique one, and C D such that yeah, and then we will call it a uniqueness quantifier. Okay, there's some different way to say it. There exists a unique one. There's exactly one. There's one and only one. Example. Okay. So there's a unique x in R such that x minus 2 equals 7. True or false? Why? Hmm? Huh? So x equal to 9 works. Okay, only 9 works. Okay. So example 2. There is a unique x in R such that s squared equal to 4. True or false? Why? Huh? Not yet. Why? X got two values that can square to 4. What are they? 2 and negative 2. Yeah. Good. Very good. You know how to show something is true or false already. Next, so this is a De Morgan's law for quantifier, right? So in the first half of the class, we learned about P without X. So now we introduce X. So once we introduce X, we need some quantifier to make sense of this PX, the sentence here. And similarly, we can take negation of it. So when we take negation of that, the existential quantifier, it will become a universal quantifier. So for some become for every. And then you need to negate the sentence itself as well. Okay, so you like bring into, okay, bring into, and then go to the back. So similarly for this negating the universal quantifier, so become a existential, and then you negate the sentence itself. Okay. So when is negation true? So for every x, you need to prove that PS is false. For every x, you need to prove that not PS is true, which is PS is false. And then when is it false? You need to find an x such that PS is true. Okay. So logic is like this. You twist here and then twist back, and then twist forward, twist backward, twist front and back. Okay. For example, you want to show that the negation of this is false, so you need to show that for every x. It's true. So you want to find an x such that PS is false. If it is false, you need to show it for every x, PX is true. Okay, so it's like twist forward and then twist backward. Okay, logic is like this. Just play around with words. Okay, let's try. Okay, actually you can prove these two equivalent statement by just using word. Okay, using word. Like what I explained just now. So try it, prove yourself. These two are equivalent, these two columns here. Okay, try exercise. Try home. Okay, so let's try and negate this example here. So when you bring this De Morgan law in, what do you get? There's this and XR such that less is less than 0. Okay. Okay. So actually there are something happening here. Okay. S greater or equal to 0 is actually x greater than 0 or x equal to 0. Okay. And then, so let me show you the more detailed work. So if we want to take the negation of this, it's actually not x greater than 0 or x equal to 0. So what is this? The negate what's this? Disjunction. So what law you need to use? Huh? The only law you need to memorize today. De Morgan's law. So you get n not x equal to 0. So you not inside, not the true statement, and then all become n. Okay, De Morgan's law. So I write De Morgan's law. Okay, so not x greater than 0 is x less than equal to 0, and x not equal to 0. Okay. So how is this the less than 0? So let me try something. Okay. So here again is this, and then I think we have a loop here. So let me see. Okay. Let me define something, right? Before we can talk about. So Q is x equal to, and then yeah. So this is like P of Q and not Q. And then this is this is P. Okay. So actually what you showing here is P or Q and not Q is actually P. Okay. So this is the general thing you can show. Try exercise again. I put an exercise here. Go and try this exercise here. So try to show P on Q and not Q is actually logically equivalent to P. Okay. Yeah, so you see, so there's actually a big step here before you write these two. Okay. Once you know this, then you can just use this. Okay, next. So, okay, I want to take negation of the existential quantifier. So what do you get? For sum become 4. Oh, okay, for every x in Z, x minus 7 is what? Negative 0. Okay, this is easy. Okay, since you see this, I think you should decide whether or not this statement is true or false. What? Someone said false. Okay, why? Hmm? Huh? Who say false? Just now I heard false. Who say false? You? Who? Who? Oh, that guy. You. White shirt, huh? Why is it false? Why is it false? Louder a bit. Louder a bit. Cannot hear. Many number what? Or many positive for x. But you need to prove me why is it false. You need to find one x for me. Huh? Wait, what's many possibility? I don't know what possibility is there. Say again. You mean 8? You mean 8? 8 8 minus 7 is 1. Hey, pass the mic to him. Yeah, what you want to do? Say again, what you want to do? 8 I tried 8 already. What's 8? 7. Oh, 7. Try 7. 7. What happened to 7? 7 minus 7, huh? Is it? 7 minus 7 then? Huh? Say use the mic. 0. Okay, take 0 and then? And then done. You happy already? Okay, so false because there exists an x which is 7
such that 7 minus 7 is 0. Okay? So it is false. Because you found some x such that when x minus 7 is 0, it's not is 0. Yeah. Okay. Okay. Okay, pass me back the mic. Okay, thank you. Thank you very much. Very good. Okay, how about this one? We haven't decided this is true or false. We haven't decided this is true or false yet. So there exists an x such that x is less than 0. True or false? True. Why? Why? -1? Okay, so take x to be -1, which is less than 0. So there exists, you just need to find me one. Okay. If you want to show that it is true. Okay, good. And 26. Next. Quick. Trend is moving. So this one. So prove that not for every x, px implies qx is logically equivalent to there exists an x, px and not qx. Okay, you can use the algebra method. Okay. The difference here is only we add in the quantifier and then we add in the variable into the statement. Okay, this is an exercise. You should do it at your own time. Okay, when you're free to read. Use the De Morgan's law to the quantifier. Also use it on the sentence. Okay. Okay. I want to go to the next one. It's more interesting. So we have more quantifiers coming in. And these are the nested. Why is it a nested? So that means the order is very important. If I write for every x in R first, that means S is already chosen. Okay. After S is chosen, then we chose Y. Okay. So the order is like this. So we choose the first one that comes first, and then we choose the next one. So it's like the nested. Okay, nested. Okay. So let's see what happens. So they have I only choose 2 variables to present here. So there are already 4 choices we can consider here. Okay. So let's read about this sentence here. So every predicate is s plus y equals to y minus x. Okay. And then I put different quantifier at the front. Yeah, let's see what happens. So this sentence here means for every x in R, okay. So when I say for every x in R, your mind should fix some x here already. Put your favorite real number in. Maybe my favorite one is 2. Okay, I put 2. In my mind, I already have 2 in my mind. So, and then next, this statement has to be true for every y. Okay. So maybe I test another 2 again. So I put 2. Test it for another 2. 2 plus 2 equals, which is 4 equals 0, which is false. Okay. I already found some x and some y such that this is false. So this statement is false. So in general, you want to show this kind of statement is true, you have to show it for all x and then have to show it for all y. So I give you one x, you need to show it for all x and all y. Okay. But there's a quicker way to check. Okay. I play cheat. Not play cheat, but
smarter way. Okay, I can show because this statement is the key point, so I can do algebra to it. So I can show you the power of algebra. So you get 2x equals 0, which means x equals 0. Yeah, this is so all these statement I can replace it with x equals 0, x equals 0, x equals 0. Okay. Of course, if you want to do the traditional way, you should do it. Okay. So exercise check the validity of the sentence without modification or without modification. Okay. So what we can do here is see this question here. For every x in R, there is a y such that x equal to 0. So I already told you s can only be equal to 0. If you pick s equal to 1 or other than 0, like 1, 2, 3, 0.1, square root 2, it doesn't work because they are not equal to 0. Okay, so this is clearly false. Okay, next, if I pick, the question said there exists one x that works for every y such that x equal to 0. Okay, so can I find such x or not? Yes, what is that x? 0. Okay, I already found x equals 0. Can I pick, what y can I pick? Anyone, right? Because y doesn't come into this equation. So if I pick y equals to 1, s still equals 0. If I pick y equals to 2, s still equals to 0. If I pick y equals to square root 2, y still equal to 0. So it is true. Okay. How about this? For every x in R, there's an x in R such that okay. There's an x in R and there's an y in R such that s equals 0. True, right? Why? What can you pick? You can pick x equal to 0 and y equal to 1 maybe. Yeah, anyone. Anyone you like. Okay. So the difference between these two is you need to check for all y here. Here you need to only just pick one. Yeah. Any question? No? No, we go to the next one. We go to the next one. Yeah, we go to the next one. Rules of inferences. So this slide you just need to understand, you don't need to like memorize. So this is just some terminology for us to discuss what we have to say in the logic. So first of all, argument. Okay. Last time we talked about statements, right? I teach you how to build a statement. Now you know you have to put those statements together, and then the sequence of statements that end with a conclusion we call an argument. Okay, so when you want to convince people, want to convey a message, these are you need to speak a whole argument before you end with a conclusion. And then we say that the argument is valid if the conclusion is true. Okay, whenever all the preceding statements are true. That means every statement you say happens and then force the conclusion, and then your whole argument is valid. Okay, and then we would say that the things before the conclusion is premises. So the idea should be like this. So you got an argument. Okay, argument is the front part is premises, and then the last part is conclusion. So everything is true, and then implies your conclusion is true. Okay. And if you give some wrong reasoning, then it's called a fallacies. Okay. And this is not too important, but some work that you need to take note. Okay, next is rules of influences. Inference, not influence, inference. So you need to infer something. So let's say you got a P, you got P implies Q, then you will get Q. Okay, this is what we discussed last time. Okay. And also, if you got P implies Q, and then you got not Q, you got not P. Why? This is the contra positive, right? Contra positive. So this is not Q imply not P. Contra positive. And everyone sign. So next one is like transitivity. So if you have P implies Q and then Q implies R, you can get from P to R. Because once you have P to Q, then you can go from Q to R. Okay. This one, P or Q, and then with not P. So when is P or Q true? If you not P is true, then Q have to be true. So you will get Q. Okay. And then P, you can disjunction with any other proposition. If you have a conjunction, you can deduce P, or you also can deduce Q. Okay, the same. We call it a simplification. And then if you have P and Q together, you will have P conjunction with Q. This one maybe not so important for now, but you can study. So why are these true? You can show that this is actually a tautology. Okay, P and not Q can implies Q. Okay. So you can show that this step is actually a tautology. That's why we have this. Okay. Yeah. Any question or no? If not, we do some example to strengthen your memory. Okay. For example, let's say I said eat, and then haven't eat, then is the negation, and then let's say food, and the negation of food is hungry. Okay. Okay. Instead, I want to write it this way. Okay. So I put a statement if I okay. How can I put it? Maybe just put it like this. Okay. Then okay, now I want you to like look at the logic of these statements. So if I ate, I told you if I ate, then I'm full. So this is my claim. Okay, I told you. Okay. So what I did, I ate. I ate. So the consequence is I'm full. So full. Okay. And equivalently, if I'm hungry, which means what? Then I haven't eaten. Okay. Something that's not equivalent is if I haven't eaten, then I'm hungry. Right? This is different. Okay. Actually, this is different. So sometimes you will think that these two actually equivalent, but actually they are not. All right. You try and think carefully. So why are they not equivalent? You are hungry. You just say that if you ate, then I am full. But if you are hungry, it doesn't mean that you haven't eaten. Okay? Maybe you go do something else. Maybe you go sport, or maybe you do hard work, and then you are hungry. But when you say if you ate, then you are full. If you ate, then that means you must be full. If you are hungry, that means you haven't eaten. Okay? But if you haven't eaten, doesn't mean you are hungry. Okay. 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 So okay. I'll give you a big picture here. So what I want to say is P implies Q is logically equivalent to not Q implies not P. But it's not logically equivalent to not P implies not Q. Okay, I think the first time I think about this question, not this question, I mean exposed to this logical equivalences. So I keep giving myself a lot of examples to think. Because sometimes in the conversation, with daily conversation with people, maybe you think that this word, but actually it's not logic. Okay? Yeah. Next. Very important, this one. Okay, next. Next. This one. Okay. So this one is also a reminder. This is more formal. So if I have this statement, for every x, px, we can deduce pc. Okay, I give you an example so that you can appreciate what is it talking about. Okay, can I get your name, please? What's your name? Huh? Shorter name. First name. How your friend call you? How to spell? Okay. Vivian. Vivian. Okay. You? Huh? How your friends call you? Ziyang. Ziyang. You? Tin Hao. Tin Hao. Okay. Okay, let's say I get these four names. Let's say this four person is all the students inside this class. Okay, so this is the Wednesday class. Okay. So if I say that every student, okay, including all of you, just that I can't say all your names, so I just put for here first. Every student in this one is the Wednesday group passes Discrete. Yeah, so every student in Wednesday group passes Discrete math. So that's mean what? That's mean yeah, that's mean okay, that's mean Yiqing passes Discrete math. And Vivian is a student in Wednesday group, right? So Vivian also passes Discrete math. Ziyang is a student in a Wednesday group or not? Yes, so he passes Discrete math. Yeah, Jin Hao also student in Wednesday group, so he passes. Discrete. Okay, so this is the universal instantiation. Okay, so I instantiate it. So every person, every student become a student. Okay, instantiate it. Okay, this is the first one. So here I put Wednesday group. My group contains who? Contains Yiqing, contains Vivian. Okay, let's say second one. So universal generalization. So my statement has to be true for every X in my set. Okay, before I can say that for everyone. So this is a invert process. Okay, it's like inverted process. So let's say first I check Yiqing. Yiqing got pass or not? Got. Yiqing passes discrete math. How about Vivian? Vivian check. Oh, Vivian also pass. Oh. How about Jin Hao? Jin Hao also passes the discrete math. Okay, last one I have to check. Ziyan pass or not? Yes, Ziyan passed the discrete math. Then I can say that every student in the Wednesday group passes discrete math. Okay. Okay, next, the third one. So the next one, there exists. So there exists. There is, or they are, maybe not so sad. There are some students in the Wednesday group passes. So if there are some, this means at least one of them pass. So if I check Yiqing, oh, Yiqing passes. Okay, then done. It's enough. Okay. Or so okay, in real life, right? In real life, you want to check some statement. You maybe want to check there are some. Okay, there are some. There's a few. So you check, and then you found actually all of them passed. So that means you can how to say, you can upgrade your statement to every. So every is stronger than the exists, right? Everyone have, but there's this only a few. So sometimes when you're doing the real life question, sometimes you can upgrade your statement. Okay? And then if you found someone in the group passes, then part 4 is you can deduce that there's a student in Wednesday group that passes this group. Okay. What time is it? Oh, 48. 2 more minutes before we jump into tutorial question. Any question for today's lecture? Any question before we go into break? This question is a lot of question. Any question for this week's lecture before we go into break? 1 more minute for you to think. Okay, if not, we go into break and then we come back at 10:59.
哎
关于刚刚那个部分，就是那个
Yeah.
interference 这个部分
呀，
其实我不太明白他到底是想要表达什么，
这个哈，
是不是？
这个，
对对对，
这个哈，
啊，
这个是说，这个是说，你有一个句子
啊，
是可以 work for 所有的 x，那你就可以直接套用在每一个 x 上面。就比如说，我这个句子是用在所有的学生在星期三的群里，那只要那个学生是在星期三的群里，他就符合这个条件。
这样子这个你刚刚因为其实你刚刚这个讲的其实好像第一个的，所以其实
这一个哈，对，他这些他就是，I think you can understand this.
yeah,
it's
okay.
Yeah, okay. I say English. So, okay. So he's asking about what are these? What's the difference between these two? Maybe. So the first one is you start with a general question, okay, and then you can apply it to a specific example. The second is you start with a specific example
In general.
and then you generalize. Okay. So to go from general statement to a specific example, you just apply to an example. But for this, to build a general statement, you need to verify for all the specific examples.
Okay. So if I want this whole statement to be true,
Which statement? Which statement?
this one, the second one.
This statement? This statement is it?
So let me make this clear first of all.
Okay.
This form is in means that PC for an arbitrary C implies all X in PX, right?
Yes. That's right.
So if I want this statement to be true, that is mean that I want the second statement be true, which is all X in PX to be true, right?
Yeah.
So even so like this, the first statement wrong also can be applied that the second statement is true and the whole statement is true.
Oh, you mean if implication is it? Okay. I mean if this is, so you mean this is Q, okay, this is P, this is Q. So this is Q, this is R. If Q imply R, Q is false. Q, R is still true.
Yeah.
Let me see how is this what it meant. This how to say
不明白这个东西到底是怎样的。
I think wait. No, I think you no, he is asking about like what's the logic line from here to here. Okay, first of all, the definition of this is for every x such that yes, okay. So that if you want to check this, you need to check for every x. Okay. So actually, this is what this is saying.
Oh, okay. Oh, yeah.
Okay.
Because the C is a part of S, right?
C is a part of X. C is a particular.
C is a subset of X.
C is not a subset of X. C is a particular example of X. So maybe I can call this XC. Not call it, but I mean take X, take C to be X. You get what I mean?
But C is not every X.
C is not every X. C is one of the X. Yeah. Yeah.
Okay, I can now understand.
You understand?
Yeah.
Okay. Yeah.
So we simplified element C as an X,
Yes.
and we
Yes.
found that there is some characteristic exists. So we see that it's universal generally.
You show that the PX is true for all the C.
Then we can define that PX is true.
Then you can say that PX is true for all X. What's your question? No, you just can't listen. Okay.
Actually, sir, I want to ask something. Last week,
Yeah, last week.
the notes you shared in the motor, right?
Okay. Yeah, which one? Oh, okay, okay.
This one, right, sir? How they prove this thing, prove this? After you get this, then I have to draw truth table. Is it?
Wait, what you do?
A copy.
The first one, right?
Yeah, the first one.
The first one you have to use truth table. You cannot use algebra.
看到没有？看到没有？跟你说了，这个是第一，
Oh, so this one is
它是用这个跟这个，
Yeah, yeah,
看
yeah,
到没有？
yeah, 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 yeah. This because you see because in this step here, P implies Q.
Yeah.
I replace with not P or Q.
Yeah.
It's actually coming from here.
So this one I use truth table to prove that I
Yes.
use this
Yes.
here.
Yes.
Then this
Yes.
one is
This part is over. What do you mean?
here is for.
What do you mean?
在问这个吗？
No, I just continue, right? I use De Morgan's law and then I use the
Oh, it's
number.
just to show can simplify to this.
Yes.
So why is
Equivalent, yeah.
equivalent to this one?
Yes.
So we can only use choose table.
Yeah, because this is the first this is the first instant where we have the connection between the implication and the disjunction. Okay. Yeah.
This one, what is this? What is this statement for? Is it to show the same source value as this? Because I checked that. Check this one is not FTTF.
You check that this is not FTTF.
The bottom one.
The bottom one?
Yeah,
The bottom one is not?
not FTTF.
It's not?
No.
Let me see. Did I copy the wrong? Okay, let me try. Sorry. So I said that. Okay, let me try. P Q not Q Q P or not Q? Not Q, not Q.
True.
Oh, this is not. So this one wrong, you mean?
Yeah.
Why?
One is all.
These are all. Is it N? N. Let me try N, P, and not Q. Why is it N? This, false and false, false. So it's true. It's also not. So what is this? I forgot from where.
Yeah, what are we going to prove already?
No, because I write out a few similar because this is right.
Yeah, or is this supposed to be one equation? Because I tried to put or between these two and it worked.
Yeah, wait, what does this work or not?
This work.
Oh, this work, okay.
Then I tried to put or after this. So this or this, and it worked.
This or this work.
This or this, yeah.
This or this work.
Yeah. So this or this.
I think I get from the other book, so I forgot already. Maybe I go back and check first. I forgot I get it from which book.
But the point is that to show that this has the same truth value as this one.
Yes. Yes. I checked. I forget I copy from where. Okay, let me check again what happened. Why I write this? I check first. Okay,
这是它的历史。
I check first.
我上一节课是 SWE 的
啊？
上一节课那个例子
哪个呀？
SWE 的，对吧？
这个哈，明天的，就是明天的，明天的，对 SWE 都没认识呢。
这个我认识，
这个，OK，
新设的。
啊，
我想问一下，这个是只能用 choose table 证实吗？
对，只能用。
那我之后就是遇到这种转换的，就是用1然后转换成这个是可以直接用这条规律差。这些不是二次推导的，都是可以直接用的。
谁？这些是哪一个？
这3个就是可以。这个是
可以直接用啊。啊，不，你要用那个 truth table 证了过后，你就可以直接用。
哦，就是还是要修正一遍这个。
对，因为这个是第一次他们两个有关系，所以你不能够直接用，所以你要先用 truth table 证过后，你才可以用。这个也是，这一个和一个箭头的有关系，它是定义，所以有点像是定义，这两个其实是定义，它是这个定义。
那就是这种我的转换的，我首先就应该想到这条规则。
对，没有错。所以这两个箭头的怎么去到这个呢？要透过这个。等你知道两个箭头跟一个箭头的关系过后，这样你就可以从一个箭头再跑到哦的下去，那你就有两个箭头和Okay, hello, testing. Okay, you can now start do the tutorial question. We will discuss in 11:20. Okay, we'll discuss. In the meantime, if you want to ask about question, you still can ask.
啊？对对对对对对对对对对。So the 1.3 is the 1.3 section in the textbook, and then it's question 2 in that section. Right? So we have 1.3, 1.4, and 1.5. Let's are you Chris Nandi? Chris Nandi, huh? Okay. Okay, Chris Nandi tried there's one example in my previous lecture notes. I think I didn't cover this in the lecture, but I just put it as my preparation and then I just share it to you. And I wrote here that P XOR Q is actually logically equivalent to this. So since this week you already learned logically equivalent, you should work out the truth table of this and then show that it's actually false. It's the same as P XOR Q. And then I also not sure why myself wrote this thing down, but I think Chrisanti checked that this is not logically equivalent to P XOR Q. So I will remove this. Maybe I want to combine these two statements at first. I'm not sure, but when I try to do this, so I use the De Morgan's law. So actually, I can't really combine these two. So yeah. So this is the another form of P XOR Q. So P or Q or N, not P or not Q. So you can show that actually these are logically equivalent. Yeah, I'll try. I think I will remove this from the slide later. I mean, I just remove it now and then I will upload a newer version. Okay. Yeah. Good. Yeah. Try all the question exercise in the action notes. Okay, let's go to this week tutorial question. Okay, so first is warming up question 1.3.2. Show that not P and P are logically equivalent. So I just do the truth table. Okay. So first, not P becomes false true, and then not P becomes true false again. So it's the same as true false. So this is good. Happy minus P is minus P. Okay, next. So next, want you to translate implication to disjunction or conjunction. Okay. So not P implies not Q is P or not Q. Okay. It's a not. So actually I skip step here. Right? So make sure you know what's going on. So in between you have not P or not Q. Okay. Not P and not Q is P by previous. Yeah. So you need to use, you want to use algebra. You can use algebra, but wait. You want to use truth table to show these two. I don't think you can just guess this answer. So it's better to use algebra in this question. Okay. So the key here. So the key here is you need to know how to go from implication, go to no single to this already. So how maybe like this. Okay, go to all and so on, negation. Okay. And also you need to know how to go from double-headed arrow to maybe arrow first, and then go to arrow. Okay. So this you need to use the truth table to prove first, and then use algebra. Okay. So let's see example here again. So P or Q implies not P. So implies how to go from implies to or. So you not the first statement or the second statement. And then from here to here, what law you use? De Morgan's law. Okay. So n become all, and then you negate both. Okay, and then this go to this is the absorption law. So you n and then all then up. Okay. If you are not happy with this line, go use truth table and prove it. Okay. And then the next one, same, just more difficult. So not the first statement or the second statement, and then you keep opening up. Okay. And then use a few times De Morgan's law. Okay, not too hard. No question? Okay, go next. So show that this is a tautology. P or Q and not P or R implies Q or R is a tautology. So this is the last one, right? The resolution law. Okay, so what you do is you just list out all the possibilities and then you compute. Okay, and then you show that the last column is all true. If you have done any mistake or not. Any question? No? Okay, next. Okay, this one is more interesting to do. Okay. So the question is, take x from the integer numbers and then look at this x plus 1 greater than 2x. Okay. Your predicate is x plus 1 greater than 2x. So check Q0. Okay. Q0 is 0 plus 1 greater than 2 times 0, which is 1 greater than 0, which is 2. Okay. Q minus 1, you get 0 less than, 0 greater than minus 2, you get true. Q1 is 2 greater than 2, which is false. Okay. D. There exists x in the integer such that qx. True or false? True. Why?
0 and negative.
Okay, like 0 and negative 1, you can pick a poison. So you want to pick minus 2, it's okay. Minus 2, you get what? Minus 2, you get minus 1 greater than minus 4, which is true. For every x, qx is true. True or false? Why?
Q1
Uh,
is the counterexample.
okay, Q1 is a counterexample, which is part C. Okay. Q1 is a counterexample. There exists an x such that Qx is false. True or false? Why? Also take Q1. Okay, same. So is this similar, different way of phrasing it? Like similar reason you can use. So for every x, Qx is false. True or false?
False.
Why?
Is Q0 and Q negative.
Okay, you got Q0 and Q negative 1, which is true. Yeah, from A and B. Okay, this is a good answer. So this is from A and B. This one is from B. This one is from B. This one is from C is from B. And B. Okay. Yeah, so there's a reason why they ask you to do A, B, C first, right? So you can check A, E, G. Okay. So in mathematics, it's like this one. If we have a series of questions, usually they are connected one. Otherwise, we'll skip the one. Okay. And next, 1.4.36. So negate for every x minus 2 less than x and x less than 3. So for every become, there's this. Okay. And then n become, De Morgan's law again. greater become less than or equal to, and then less than become greater or equal to x. Right? Okay, next one. Not for every x, 0 less than or equal to x, n less than 5. So negate for every become there's this, and then n become oh, and then negate. Just keep repeating. Negate for every become negate the exist become every, and then n become oh, and then less than equal to n greater than equal to become less than, and then less than equal to become greater. Okay, this last one also the same. Negate the exist become every, and n become oh. Okay, maybe see whether they are true or false. I think this one is more interesting. So A is true or false? I haven't done yet actually. So we should do it. So A is true or false? Huh? True? True. True. So what's the number that is less than equal to 2? Yeah, true. True, right? True, right? I can take x equal to -3. Never mind, because even this is false, this is still true, right? So I also can take s equals to 3. Yeah, so this is true, this is false, never mind, it's all. Okay. Okay, let's try the second one. True or false? Also true, right? So s can be what? -1. Also, s can be 5. Also can 6. Also can. Never mind. How about C? True or false? Huh? True. False. Why false? Take x equal to -1. So what happened? So -1 is greater or equal to -4. So false first one. -1 is greater than is less than 1. So also false. Okay, right. So all false. So you found an x such that x is greater than -4 and x is less than or equal to 1. Okay, which is x equal to -1. Okay, so D, true or false? False. Why? Take one. X equal to 0. Okay, let me try. So -2. So let me try 0 first. So 0 is greater than -5. 0 is less, wait. 0 is greater than equal to -1, right? So 0 doesn't work. So let me try -2. Okay, -2 is greater than equal to -5. -2 is less than -1. Yes. So both of them false. So that means there is an x where x is equal to -2 such that x is greater than -5 and less than -1. Okay? Everyone follows? Okay? Yeah. Okay, next. Okay. So 1.4.52. Show that for every x px or for every x qx is not logically equivalent to for every x px or qx. So this is to show that something is not logically equivalent, you just need to give a counter example. Anyone got any counter example? Huh? Do you have one? Do you have answer? Do you have answer? Do you have answer for this question? What's your counter example? What's your counter example? What's your answer? What did you write? You don't know how to say?
Yeah.
Let me see. Q is not equal to, Q is X not equal to X. What is X? There's no X that is not equal to X. Right. Right. Other got answer or not? Any answer? Okay, I got one answer is for every X in R, okay, your PX is X is less than equal to 0 or X is non-positive or S is positive. Okay. But if you split them out, for every X, X have to be non-positive, and for every X, S have to be positive is false, right? Is it true? But these two, true or false? False, right? Because one is greater than 0, and then in this case, you can pick X equals to what? 0. 0 is equal to 0. It's not greater than 0. Or if you want, you can pick X equal to -1. -1 is less than 0. Okay? Happy or not? Happy? Not happy? Why? Why not happy? Ah. Okay. Hey, make sure you ask if you're confused. Okay. Also, textbook answer, I think they use integer. So all the integer is either odd or even. Okay. So if you split it out, then you also get a similar type even. Okay. Not all integer are odd, not all integer are even. So I think the harder part should be the more restricted part is this one, I think. And then this one left. Okay. Next, I think 1.5.4 is a bit boring. So if you can write out, then should be good. So there's this, so some, there's this for every, so some, then every, and then for every X, there's this Y, so every student have at least one course. See, there's some trick here, so they sort the order. So there's this Y for every X here. So there's this one, so you fix your course first, and then every student get it. And then here also, you fix the courses first, every courses that is taken by one student. Okay, and then so the order is very important, and also the quantifier is very important. Order of quantifier is more important. Order of variable is also important. Okay. This question, just like this. Okay. No question. We jump. The next one. If you want to refer back later, I will show you. Okay. See how many students. Last one. Okay, let me go. Eight. Okay. So, wait, what's only working on? Yeah. Okay, in the meantime, you can think any questions you want to ask. Okay, so 1.5.28, we pick x and y from the real number, okay? So the first question is, for every x, there is the y such that x squared equals to y. So is it true or false? True. Why? Why is it true?
That's 4 x as 2, y as 4.
Okay, wait. So you say you take x as 2, y as 4. So you get 2 squared equal to 4, right? But how about x equal to 3? What happened? Y equal to 9. Is it? Yeah. But I want to prove for all x, right? So I give you an x, you have to give me a y. So how? Huh? So this means this y have to depend on x, right? So you need to take y to be x squared. Okay. So why x squared works because x squared live in R. So y is in R. So this kind of question, right? For every there exists or there exists, you need to find me the y. You need to tell me what y I take. Okay. So in this question, I take y such that y equal to x squared. Why it works? Because if you multiply the two real number together, I still live in real. So this is a number inside my domain. Okay. Okay. Please stop me if I'm too fast. Okay. Second question, for every x, there exists y, s equal to y squared. False. Why is it false? Huh? So you take s equal to -1, what do you get? -1 equal to y squared. So y equal to square root -1, which is not in R. Okay. So this is actually in the complex world. So to show that it is false, okay, you need to find me an x such that for every y, this is false. Okay. Okay. C. There exists an x for every y such that x y equals 0. True or false? True. Why? Yeah, we take x as 0. Then what number you multiply with 0, you always get 0. Okay. D. There's this x, there's this y such that x plus y not equal to y plus x. True or false? Why? Huh? Why? What? Commutativity. Okay, actually this is by definition. So addition of real number is commutative. In fact, all the number systems should be commutative. So all the addition are commutative. So when you add two numbers, it's always the same if you add the other. So actually, these are the property we give to the number. It's not come for free one. So if you do like addition in the high school maths, right? So they are actually commutative. 2 plus 3. Okay. E, for every x not equal to 0, implies there exists a y such that xy equals to 1. True or false? Why? So you need to find me a y, right? There is a y, so you need to find me a y. What y you should take? One? What? Take y to be 1? Wait. I want to discuss this. So take y to be 1. So if I put x to be 2, then 2 times 1 is not 1 anymore. Huh? You have to take y to be 1. Yeah, 1 over x, right? So if you give me an x, which is not 0, then I give you a y, which is 1 over x. Then we multiply together, we get 1. Y and also 1 minus x is defined because x is not equal to 0. If 1 over 0, undefined. Okay, so 1 over x works. Okay. Next, for every there's just an x for every y such that y is not equal to 0 implies xy equal to 1. True or false? True. False. Oh. False. Eh. You know why false? Because if you pick maybe okay. So for every x you give me, I can produce a y for you such that xy is not equal to 1. Okay. If you give me a number x, I just take y equals to 2 over x. Okay. When I multiply them together, I get 2. So the most important thing you want to check is the thing behind here, okay? The predicate here. So if you want to make it not true here, you need to think out of a way how to make x, y not equal to 1. Okay. And then my way is to take y equals to 2 over x. Okay. Similarly, you also can take y equals to 3 over x, y equal to 100 over x. Okay. So when they multiply with x, they won't get 1. Okay. So next, for every x, there is an y such that x plus y is equal to 1. True or false? Huh? True or false? Huh? True. True. So if I say this is true, I need to find a y that works for all x. So I just take y equals to 1 minus x. I just play around with this number. 1 minus x is still a real number, so that's fine. Next, h. There's this y such that x plus 2y equals 2 and 2x plus 4y equals 4. Okay, so how to do this? How on earth are you going to do this? So this is actually the simultaneous equation. So try to play around with these two equations because you want both of them to be true. So you can do the substitution, multiplication. Okay, and then you will get something like 0 equal to 1, which is wrong, which is contradiction. So that means there's no x or y you can put in such that 0 is equal to 1. Okay. So this is false. Okay, false. H is false.
X plus 2.
You mean huh?
Huh?
And then
The two statement is their multiplication, right?
oh yeah, also can, yeah. You see? Yeah, right. So you said these are 2, so 4 equals to 5, is it? Okay, yeah, it's the same. 4 equals to 5 or minus 4, yeah. So if my minus 4 from each side, I get 0 equals to 1. Yeah, same. Yeah. Yeah, maybe faster. This way is faster, yeah. So you get only 2 lines. Okay, good, very good. Yeah. The idea of coding is to make it efficient. Okay. Next, for every x, there's this y, x plus y equals to 2 and 2x minus y equal to 1. And then you also use the same way. And then actually you found out that this statement here is equivalent to s equal to 1. Okay. So if it is worked for OX, then it's false because only x equal to 1 works. Okay, this is a bit similar to what the example I gave just now, which is equivalent to x equals 0. Okay, last one, J. For every x, for every y, there's a z such as z equal to x plus y over 2. So true or false? True. True. So you need to find me a z. So what's z? You just take x plus y over 2. Okay. So x plus y over 2, you need to show that it is a real number. So why is it a real number? Because you add two real numbers together and then you multiply by half, which we call the scalar multiplication. So real numbers are closed. Okay, these are the property. Closed under addition and scalar multiplication. So it's true. So you just take z equal x plus y over 2. Any questions? If not, then we dismiss for today.
Thank you.